Chapter 3, The Experiments of Hertz. The first direct experimental confirmation of Maxwell's theory of electric waves was made by Professor Heinrich Hertz of Karlsruhe in 1888. At Karlsruhe and later at Bonn, Hertz performed a great number of experiments in which he produced and detected electric waves, measured the wavelength, showed that the electric waves were transverse, polarized waves, that they were capable of reflection from metallic surfaces and were freely transmitted through insulators, that they could be refracted by prisms of pitch and other dielectrics, and that as the wavelength of the electric waves was shortened, the electric waves showed properties more and more analogous to the properties of light. Lodge's resonance experiment. Prior to the work of Hertz, Sir Oliver Lodge in England had made some experiments on the inductive action between Leyden jar circuits, which were a close approach to the discovery of electric waves. A description of these experiments will aid us to understand Hertz's apparatus. Lodge employed two circuits of the form shown in Figure 22. The Leyden jar A had its two coatings connected with an electric machine, so that when the machine was operated, the jar was charged, and when the tension of the charge reached a certain value, a discharge occurred through the loop BCD and across the spark gap S. This discharge was oscillatory and acted inductively upon a second circuit A prime B prime C prime D prime placed parallel to the first. The second circuit was provided also with a spark gap at S prime, which was formed by a strip of metal folded over the jar so as to touch the inner coating and come near the outer coating at S prime. This circuit, which we shall call the receiving circuit, had its period of oscillation variable in that the inductance of the circuit could be changed by the movable slider at C prime, D prime. When sparks were passing in the discharge circuit, Lodge found that there was a certain position of the slider C prime, D prime that gave a maximum effect at the receiving circuit, as was shown by the lively passage of sparks. Across the spark gap at S prime. The two circuits were then in resonance, that is to say, they had the same period of oscillation as determined by the formula T equals 2 pi times the square root of L times C. The oscillatory current in the discharge circuit induced an electromotive force in the receiving circuit, and when the circuits were in resonance, this induced electromotive force was capable of forcing sparks across the gap at S prime, even when the two circuits were several meters apart. According to Maxwell's theory, the inductive action between the two circuits consisted of electric waves sent out from the discharge circuit and striking the receiving circuit. But Lodge was not able to demonstrate the existence of these waves. To do this, it was necessary to make the wavelength shorter and the radiation freer than that produced by Lodge's discharge circuit. Hertz's experiments with electric waves in air. In order to produce shorter waves than those employed by Lodge, Hertz made use of a discharge system with smaller capacity and self-inductance. One form of Hertz's oscillator is shown in Figure 23. It consists of two flat metallic plates 40 centimeters square, each attached to a rod 30 centimeters long. The two rods were placed in the same line and were provided at their nearer ends with balls separated by a spark gap about 7 millimeters long. The oscillator was charged from the secondary of a Ruhmkorff coil J attached to the rods near the spark gap. The primary of the coil was fed by a battery and contained a vibrator for interrupting the primary current so as to produce a high potential in the secondary. At each interruption by the vibrator in the primary, the two halves of the oscillator became charged and discharged in an oscillatory manner across the spark gap of the oscillator. At each spark, according to Maxwell's theory, there was sent out a train of waves from the oscillator. In order to detect these waves, Hertz employed a receiving circuit, now generally called a resonator, of the form shown in Figure 24, which is seen to consist of a circular loop of wire broken by a diminutive air gap at X. The radius of the loop was 35 centimeters, which was found by experiment to be the proper size to be in resonance with the oscillator. To demonstrate the existence of the electric waves, Hertz made use of the phenomenon of interference. The arrangement of apparatus is shown in Figure 25. M is a metallic reflector consisting of a sheet of zinc 2 meters wide by 4 meters high, from which the waves sent out by the oscillator are reflected. The reflected waves superimpose upon the direct waves, producing in the region between the oscillator and the metallic reflector certain positions where the direct and the reflected waves neutralize each other and certain other positions in which their effects add. In demonstrating these effects, Hertz performed a number of beautiful experiments. In one experiment, the plane of the resonator was kept parallel to the reflector, with the spark gap at the side, as shown in Figure 25. Then, wherever the resonator may be placed along the line SN1, the electric force F and F' is the same at the two sides of the resonator, but the force F' being applied to a completely metallic part of the loop acts to a greater advantage than the force F, so that sparks are produced unless both F and F' are very small. With this orientation of the resonator, Hertz started with the resonator at N1 close to the reflector and moved it gradually away toward the oscillator. In the position N1, there were no sparks in the resonator, showing that there is a node of electric force at the reflector. This result is consistent with the fact that a large difference of potential cannot be set up in the surface of a good conductor. As the resonator is moved away from the reflector, sparking begins in the resonator, becomes more and more lively until a maximum is reached at L1. This position L1 is called a loop of electric force. On proceeding further in the same direction, a second minimum of sparking is found at N2 and so forth. Discussion of this experiment. The occurrence of maxima and minima in the region between the reflector and the oscillator is evidence of the undulatory nature of the disturbance, and the distance N1, N2, or L1, L2, is the half wavelength. To make this proposition clear, reference is made to Figure 26, which shows several drawings of the direct and the reflected wave and the resultant obtained by their superposition. The reflecting mirror is represented by the heavy vertical line at the right. The undulating line, made up of dashes, represents the direct wave which is moving toward the reflector, and the dotted wavy line is the reflected wave moving from the reflector. The heavy line in the diagram is the resultant effect obtained by adding the two waves. The distance from one crest to the next similar crest, C3 to C1, is called the wavelength, and the time for the wave to move one wavelength is called the period t. The different diagrams, A, B, C, D, E, F, G, H, I, show the conditions that exist in the region between the oscillator and the mirror at different times. At a time that we have called t equals 0, as represented in diagram A, the direct and the reflected waves are exactly opposed to each other throughout the space between the oscillator and the reflector, so that the resultant electric force is everywhere 0. In B, t equals t divided by 8, the direct wave has moved nearer to the mirror by a distance equal to 1/2 of N1 L1, which is equal to 1/8 of a wavelength, while the reflected wave, which moves with the same velocity, has moved from the mirror by an equal amount. It is seen that now the direct and the reflected waves do not oppose each other everywhere in the region. In some parts of the region, for example, at N1, N2, N3, they do oppose and neutralize, while at L1, L2, and L3, the added resultant about 1.4 times the maximum of either wave alone. In C, t equals 2t divided by 8, the direct wave has approached the mirror by another eighth of a wavelength, the reflected wave has receded from the mirror by an equal amount, and the two waves exactly superpose. The resultant intensity of electric force is still 0 at N1, N2, N3, and N4, while at L1, L2, and L3, the intensity is double that of either wave separately. In a similar manner, the remaining drawings, D, F, G, H, I, represent the progress of the direct wave toward the mirror and the recession of the reflected wave from the mirror by successive eighths of a wavelength. The resultant intensity is always 0 at N1, N2, N3, and N4. On the other hand, if we pass down the figure from diagram A to H, we see that the intensity at L1, L2, and L3 begins at 0A, rises to double the intensity of the single wave, C, falls to 0E, then to minus the double intensity, G, and finally at the expiration of a time equal to T, rises again to 0, I. To show this more clearly, all the resultants are collected in the last diagram of the figure. The positions N1, N2, N3, and N4 are the positions in which the resonator of Hertz gave no sparks at the detecting spark gap, because the electric force at these positions is constantly zero. The positions L1, L2, and L3 are places where the sparking at the resonator was a maximum, because at these places, the electric force fluctuates up and down during each period of the wave. The distance from N1 to N2, or from L1 to L2, is half the distance from C3 to C1 in diagram A, and is therefore equal to half the wavelength. With the dimensions of the apparatus used by Hertz in the experiment represented in figure 25, this half wavelength was 4.8 meters. The set of drawings given in figure 26 represents the conditions that exist in a stationary wave system, in which the direct and the reflected wave are both moving, while the interference between these two waves gives a set of maxima and minima fixed in space. The minima are positions where there is never any resultant force, while at the maxima, the force fluctuates between positive and negative maxima with a period equal to t, the period of the waves. The conditions assumed in the drawings given in figure 26 are somewhat simpler than the conditions actually occurring in Hertz's experiment, because the direct and the reflected waves in the case represented in the drawings are supposed to have the same amplitude, whereas in the actual experiments, the reflected wave is weaker than the direct wave, so that N1, N2, N3, and N4 are not positions of zero intensity, but yet have intensity small enough to enable them to be located by the experiment. Nature of the wave. The experiment by Hertz, just described, shows that the disturbance sent out from the oscillator and detected by the resonator travels as a train of waves. To give the reader an idea of the nature of this wave motion, reference is made to the diagram of figure 27, which shows in part the electric field about the oscillator at a particular moment. This figure is a simplification of a diagram theoretically obtained by Hertz from Maxwell's equations. The oscillator is shown in the center of the diagram, and on either side of the oscillator are shown the lines along which Maxwell's displacement currents occur. These lines are called lines of electric induction. We have seen in Chapter 7 how we can imagine the displacement current in the dielectric to complete the conduction current in the oscillator. In that case, the lines of electric induction terminate on a positive and a negative charge at their two ends. At the instant represented in the diagram, the two halves of the oscillator have opposite charges, and some of the lines of electric induction near the oscillator terminate upon the charges on the oscillator. But a little farther out from the oscillator, the lines in the diagram are represented as closed upon themselves. This closing of a loop on itself occurs when the positive and the negative charges on the oscillator come together as the current in the oscillator reverses. The closed loops represented in the diagram have been produced by successive oscillations of the current on the oscillator and have been liberated from the oscillator and are moving freely away. The condition of things in the space around the oscillator in action may be pictured to the mind by supposing that these closed loops of electric induction move away from the oscillator, and as they move, they elongate and grow less intense. Their width, however, remains constant, so that if a receiver is placed in any fixed position, say in the equatorial plane, pp, the inductive action of the loops as they successively pass changes continuously from one direction to the other, with a period equal to that of the oscillator. This train of continuously reversing electrostatic induction is one aspect of the electric wave train. Another aspect of the electric wave train may be discovered by examining the magnetic field about the oscillator. The lines of magnetic force about the oscillator are circles in a plane perpendicular to the oscillator, and these lines in a non-magnetic medium are everywhere perpendicular to the lines of electric induction, so that the receiving circuit, placed, for example, in the equatorial plane, experiences also a series of continuously varying magnetic forces, which tend to induce an electromotive force in the receiving circuit in the same direction as that induced by the electric induction. Thus, Both the electric and the magnetic effects act together and are called the components of the electric wave. One component is electric induction, which is in the plane of the oscillator. The other component is magnetic force, which is perpendicular to the electric induction. Both of these components are perpendicular to the direction of propagation of the wave. That is to say, the wave is transverse. Attempt to determine the velocity of the wave in air. Hertz attempted to determine the velocity of the wave. We have seen that he found the wavelength, lambda, to be 9.6 meters. This is the distance traveled by the wave during the period of one oscillation of the current in the oscillator, so that if we knew the period, t, we could calculate the velocity by the equation v equals lambda divided by t. Hertz attempted to obtain the period, t, of the oscillator by calculation from such formulas as could be had for oscillators of this shape, and he obtained the period of complete oscillation to be 2.8 millionths of a second. This gave for the velocity of the waves the value 340,000 kilometers per second. In this calculation, as Professor H. Poincaré pointed out, Hertz made an error and overestimated the period in the ratio of the square root of 2 to 1, so that with this correction, he would have obtained the velocity of the waves to be 480,000 kilometers per second, while the velocity of light is 300,000 kilometers per second. This apparent discrepancy between the experiment and Maxwell's theoretical conclusion that the velocity of the waves is equal to the velocity of light was due, as Hertz suggested, to the inapplicability of the formula used in the calculation of the period of oscillation. Experiments, which we shall soon come to discuss, show that the velocity of the electric waves is the same as the velocity of light, and thus confirm Maxwell's predictions.